Okay, if this is our graph of rolling distance versus proximity to the magnet for the cart being accelerated by the magnets or the toy car being accelerated by the magnets, that could be relabeled as work. You just take the frictional force on the car and multiply it by the distance, and you get the work done to stop the car. Which means you get an indication of how much work the magnet did on the car. So if the graph is like this would be a graph of the potential energy, U of x, potential energy of the magnet system at separation x. Take your graphs that you made, the graphs look pretty good, okay? And you get a pretty decent graph, at least over a certain range, of the potential energy for those two magnets brought into the proximity. Of course, oriented so that they're repelling. Then, the question is, can you estimate potential energy of this system at 2 centimeters and 3 centimeters? Or the change of potential energy between 2 centimeters and 3 centimeters? Well, at 2 centimeters, your potential energy is this. At 3 centimeters, your potential energy is this. Your change in potential energy, your delta U, is this. And if the scale is, as I say, and this is fairly realistic scale, okay? It's fairly realistic scale for the data that you obtain, but you can use your own data, and I want you to use your own data to make your own estimates. Okay, so on the scale where this is 0.04 joules, and I make no guarantees about the shape of this curve, I just slop the curve down there. Your delta U is this. Looks like its magnitude is about 1/4 of this. So ballpark 0.01 joules. I'd actually say magnitude 0.09. And the delta U is, of course, negative. This means that the magnet system, excuse me, loses 0.01 joules from the 2 centimeter to the 3 centimeter separation. So the car gains this. Now what happens to the potential energy the car gains? It gets lost to friction, which of course is how we got these numbers to start with. All right. So the question then is, what's the average force between 2 centimeters and 3 centimeters? Okay. Well, delta U is a change in potential energy, right? Which is the work done, you know, the change in well, okay, it's the work done by the net force between the 2 centimeter and 3 centimeter position. Okay? Or it's equal and opposite to the work done by that net force. By the conservative force, the magnetic force, sorry. The work between A and B is the work from A to B. That's equal to the average force times delta S. What's the work from A to B? Well, the work done by the magnet system from A to B is 0.01 joules. So we know the work from 2 centimeters to 3 centimeters. What's your displacement? It's a centimeter. Okay? Can we determine the average force? Well, we sure can. Okay? And we find the average force is about a Newton. Okay? Then we pulled out this apple that I brought for lunch. Hadn't planned that. You know, it fell in my head when I was coming to work. So had to bring it along. And this apple, coincidentally, has a weight pretty close to 1 Newton. I'm guessing it's a little big for a 1 Newton apple, maybe 1.3 Newtons, something like that. Pretty close. So the weight, force exerted by gravity in this apple is pretty close to the force exerted by those two magnets. Force of repulsion, if you orient them correctly, at a distance somewhere between 2 and 3 centimeters. Well, big thing here. Okay? This is a big payoff for all our agony for an hour here, an hour and 20 minutes. Okay? Yeah, let me comment. But people immediately did the second problem on this list. Okay? Which involved exactly the same reasoning that this does once you get the 0.01 joules. Okay? It's identical. And everybody did that intuitively, right? Well, it's because you get wrapped up in all the details of the problem. You don't know where to turn. Okay? But it should be pretty obvious to you that once you have this, and then you take the 1 centimeter distance and you determine the average force. Okay, well, on the graph, where's that 1 centimeter distance? There's your 1 centimeter distance. Displacement. That's your delta S. Here's your delta U. What's the slope of this segment here? It's delta U over delta S, which is equal and opposite to your average force. Conclusion, slope of the U versus X graph is negative f of X, the negative of the force exerted by that magnet, or by that magnet system. So all I have to do to get a graph of force versus X is say, well, somewhere between 2 and 3 centimeters, maybe halfway between, but not really because everything isn't quite linear. I have a force of 1 Newton. So somewhere in here, you know, somewhere around this point, okay? If I want the force actually at the midpoint, I'll make a tangent line because the limit of your delta F over, or delta U over delta S is f of X, okay? That is limit is some fancy letter goes to X of okay, some kind of a limit anyhow. That's it. And it's negative that limit, which is the slope, instantaneous slope of the graph. So to get a graph of force versus displacement, you simply estimate the slopes of a series of tangent lines. And those slopes give you the force versus distance. I'll go into more detail. But that's pretty much it. And the slopes of the tangent lines are the values of the derivatives of this function, so your force is the negative derivative of your potential function with respect to x. And that, as it should be, because your potential function is the integral of your force with respect to x, okay? And integral, depending on what your initial point is. So you go back to the first problem, the derivatives of all those quantities should be the forces. And the integrals of the forces would then be the expressions you get, okay? And that pretty much ties together almost everything in this set of problems, okay? You really want to tie that together. Make your life much, much easier over the next couple of weeks, okay? So work on it.